Computer. All right. So I'd like to welcome everybody to the April meeting of the Delaware Astronomical Society. So greetings. We have Jessica Wu this evening, and we have a lot of really interesting things to do. So first of all, I'd like to welcome any new members. Any new members want to introduce yourselves?
Well, I could. I've actually been a member for a little while now, but this is my first meeting I've been able to join, and I'm excited to hear the lecture by Dr. Liu. My name is Reed, super into astronomy, astrophotography, so I might ask about the AP SIG group. I'm happy to be here.
Awesome. Welcome.
Nice. Welcome.
Welcome, Reed.
Welcome,
Thank you.
Reed.
Thank you very much.
Any others? All right, well, if there's anybody else, welcome to the club. Sorry if you didn't want to introduce yourself. Feel free on a Tuesday night to, on one of those informal Tuesdays, you can come in and introduce yourself. It's a lot more informal, maybe not as much pressure. So the first thing we're going to do that's kind of important is our elections introduction. So Sydney, can you give us that little intro?
Yeah, sure. Thank you very much, Rob. Much appreciated. Good evening, everyone. As you know, elections are coming in. Our election month is going to be on May. And this is actually the last hour, you can say, for nominations. And the nomination is still open. As of the moment, we have 3 nominees. And you can look it up in Zoom. Bill Hannigan, David Grosky, and Tom Harding. And if you are seriously still interested in running for board members at large, it's still open until the end of this session. Just I'll probably send a chat for a reminder, and just respond to that chat if you're still interested, and we'll see. Thank you very much. That's about it. Thanks, Rob. Appreciate it.
All right, and if you guys didn't know, the elections will start on about May 1st, and Sydney will be sending a ballot with all the information about that. And then you'll just need to vote before the 31st. And then we'll finish up the election, and then they start, is it June 1st, Sydney? Yeah, okay, very good. All right, next item is the AP SIG. This coming Saturday at 1 p.m. Bill Hannigan will send out details of that to the groups.io. Do you want to say anything, Bill?
The general announcement goes out probably Wednesday or Thursday, and then the invitation goes out on Saturday morning to the people who respond. Okay, and the AP SIG mailing list.
And Reed, as just a heads up, I'm not sure how plugged in you've gotten, but a lot of our club communicates via this groups.io. Do you know if you've plugged into that yet?
Yes, if that's the general email, that's a notification for this. Besides that, I don't have anything specific for AP SIG, but that's as far as I know.
Yeah, no, so this invite did not come through the groups.io. So what I'd suggest is go on the website, and there's a section for how to do that, and that is what Bill will be using to reach out. So if you're interested in the AP SIG, you'll want to get plugged into the groups.io.
Right, and you can just go ahead and send me an email, and I'll put your name on the list.
Fantastic. Thank you very much.
Okay.
Cool.
Awesome. All right, next thing I should let you guys know about is that the telescope loaner program is going to be starting back up really soon. We've got some new eyepiece sets that we ordered up. We got some really nice Pelican cases. Jeff, can you point to those? They're right behind him in the background. If you can see them, they're in his video. And we've got some nice lettering on those cases, labeling them so that they're properly matched up with the equipment, so we avoid some problems we've had in the past. And we have embroidered the words on the bags as well. And so very soon, we should be ready to loan that equipment back out again. Another interesting item is that we were discussing in the board meeting the possibility of having a different kind of event. So we've been having some member star parties now and again. I went to one of those up at Blue Mountain Vista Observatory, and we've had a couple of those along the way. But we might be thinking about having a picnic, and we were probably going to send out a survey later this month, seeing what kind of interest there might be in doing that. And it does sound like a really cool idea. So we'll be discussing that more over the following month, and hopefully we'll make some decisions about that. It would probably be in June, And Rick Spencer is possibly going to be inviting us to his house, or we might consider another venue as well. So we got some interesting possibilities there, and it could be really fun to actually get out and see people in an outdoor setting, socially distanced, but it could be very nice, definitely. So look forward to that. Next item, Greg, can you tell us about the eclipse coming up?
Let me unmute. June 10th, early morning, there is an annular eclipse coming up. What we will see here in Wilmington, Delaware will be a partial eclipse, and it will happen right at sunrise. In fact, it will be just slightly past its its maximum coverage when the sun rises here in Wilmington, which on June 10th would be 5:35. The last contact will be 6:30, so we'll have about an hour to view a partially eclipsed sun as the moon moves off of the surface, and then the sun is fully exposed again about 6:30 in the morning. So it's an early morning sunrise event, and you need a wide open eastern horizon out over the ocean if you go to the beach, or we're talking about the possibility of getting DAS to have permission to go over to the Fox Point Park, where we have a view out over the Delaware River. There'll be more news coming up as that gets formed up as to where the location will be. But it will be a DAS member event, not a public event. June 10th.
Very good.
Get up early.
Sounds wonderful. All right, are there any other announcements? Because that's all that was on my list. Great. So Jeff, you want to introduce Jessica Liu?
All right. So actually, before I do that, a little bit peek into the future. Our May meeting actually came about per club members' request. Professor Judy Provenchal from the University of Delaware will be giving a talk on the oh geez, what's the program called? Come on, brain.
Whole Earth Telescope.
No, the consortium that we're a part of.
Sarah?
Yes, the Sarah Telescope program where we have, it's like a consortium of telescopes around the world.
Right.
See, I need to attend the talk, and then I believe she's going to also tie into that an update or the plans for the construction of this new telescope at Mount Cuba. So that'll be the May meeting, and then to wrap out our season in June, I want to plant the seed because I would like to do another round of member mini talks. So obviously, maybe in the next month, I'll start bugging you a bit more, but it's never too early to start thinking about if there's a talk you'd like to give. And again, it could be 2 minutes, it could be 20 minutes, and it could be as formal as running through a PowerPoint deck, or it could be as informal as just chatting or sharing a few photos. So start thinking about if there's something you'd like to share at the June meeting, which will be member mini talks. But that's the future. To jump into the present, tonight we have the really cool opportunity to hear a talk from Professor Jessica Liu. She's a professor at the University of California, Berkeley, and is interested in stellar birth, stellar death, black holes, et cetera, et cetera. Really cool experience because she was working with Professor Andrea Ghez, who was Jessica's former advisor, who was awarded a Nobel Prize. So that's pretty exciting. But tonight, Jessica is going to be talking to us about black holes. Again, a typical logistic, but it begs the reminder. First thing is, as we jump into Jessica's talk, Rob will mute everybody. And we kind of request that everybody remain muted, and that way Jessica's talk will be prominent and clearly understood. And we would encourage questions to be raised using the chat function of Zoom. So if you do have questions, by all means, type them into the chat section. And if other club members have the answer to those questions, by all means, go ahead and answer them. But if it looks like there's a lingering question, Rob or I will interrupt Jessica and pose the questions, just so we don't have a cacophony of everyone talking at the same time. And then once the talk is over, we will open it up and allow for a little bit more personal one-on-one for people to unmute and ask any lingering questions directly. So with that, Rob, if you want to go ahead and get everybody muted, and Jessica, we welcome you to the DAS meeting and look forward to hearing about black holes.
All right, 1 second.
Thank
Click the
you.
mute button. Hold on. Mute all. There we go.
All right, can you hear me now?
Good.
And can you see the slides?
Yep.
Great. Okay, thank you so much for the invitation. These kinds of talks, especially to astronomy groups, are just my really fun part of my job, I have to say. And questions are definitely welcome and encouraged. That's also the most enjoyable part of this experience, is if you ask more questions. So I'm going to be talking to you today about hunting for black holes using laser-guided adaptive optics. So this is a project that's both at the forefront of astrophysics and the forefront of astrotech, the technology we use to study the universe around us. And that makes it both challenging and especially fun for those of us who like to work with hardware and push our facilities as far as they're capable. Okay. All right, so let me start with a little baseline here. I hope most of this is known to some of you, but I want to make sure we all are on the same footing. So let's start with the basics. What is a black hole? From this artist's rendition, you can see it's a black spot on my screen, and it's doing something very funny to the light of the stars around it. That's a reflection of its gravity. But if we step back a little more formally, a black hole is really just a place in space where you have some amount of mass in an infinitely small volume. And as we know from in physics, this is what's called a singularity. It shouldn't be physically possible to truly put some amount of mass into infinitely small volume. Anytime a physicist says the word singularity, we should all be concerned, because that's a sure sign that we don't know what we're talking about. So black holes really are signposts for where our knowledge of physics begins to break down. It's the place where theories of gravity and theories of quantum mechanics haven't been merged and don't know how to play nicely together, at least in our model of the universe. The universe itself has figured it out, of course. Now, black holes come in a few different varieties. There are the ordinary black holes, if they can be called such a thing. These are the product of the death of a massive star. So whenever you have a star that's 20 or 30 times as massive as the sun, it exhausts its fuel and its core, and it collapses under its own gravity and turns into, we think, a black hole with a mass that's maybe 3 to 5 times as massive as the sun, or more than that. So our own sun won't turn into a black hole, but stars that are 20 or 30 times bigger may. These ordinary black holes were actually first predicted by theory, and later we've observed a few, just a handful in our own galaxy, usually accreting from another companion so that we can see them. The predicted number of black holes, these ordinary black holes, just in our own Milky Way galaxy alone, is somewhere between 100 million and 1 billion. So they should be quite prolific. Another variety of black holes, the supermassive black hole. These are the kinds you find at the centers of galaxies. These are behemoths. They have masses of 1 million to 1 billion times as massive as the sun. And they were actually first suggested from observations, not from theory. And these days, we think almost every galaxy should have one of these supermassive black holes at its heart, including in our own, which I'll talk a little bit about the discovery there. So how do we find black holes? These black holes have gravity that's so strong, not even light can escape. So they themselves don't have photons, don't shine light out that we can see. So how is it that we would go about finding them? Well, I'll talk about the two varieties. I'll talk about the supermassive black hole first and how we found the one in our own Milky Way. This was indeed the resulted in a recent Nobel Prize, both from our team led by my former PhD advisor, Andrea Ghez, and by my now colleague, Reinhard Genzel, here at UC Berkeley. The prize was shared with the theorist Roger Penrose for the discovery of black hole formation and its prediction from general relativity. And then the two observers, Reinhard Genzel and Andrea Ghez, and their respective teams were the ones to discover the black hole at the center of our own Milky Way. So how did we do that? Well, the very first thing we needed to find the black hole at the Milky Way was to not look at optical wavelengths. Our eyes aren't going to be good enough to find a supermassive black hole in the Milky Way. And this is why when you look up at the sky in optical filters or with your eyes at night, this is what you see. You see a dark band toward the center of the Milky Way, not the center, a bright center of the galaxy. And that's because in our edge-on Milky Way galactic disk, it's filled with dust and gas that obscures all of those optical photons and prevents them from getting to us. So in fact, only 1 out of every 10 billion photons in optical light makes it to us from the center of the galaxy. If we can instead turn on our infrared eyes or infrared detectors and cameras behind our telescopes, we can see a much clearer picture. 1 out of every 10 photons now makes it to us. And we can see now the reasonable structure of the Milky Way with a central concentration of stars and this thin disk that we live in. And now we might know where to look for a supermassive black hole right in at the middle of our galaxy. So we need to do that with infrared light, but infrared light's not good enough. This is an image from the 2-mass telescope. If you zoom in on the center of the galaxy at infrared wavelengths, you can see how crowded it gets. And in fact, in this most zoomed in picture here, you can see now we can't even resolve individual stars anymore. And this is with a fairly large telescope from the ground. It's a 3.5 meter telescope. And yet it's not good enough. It's not good enough to see in and see individual stars separated from each other right in the middle. So we have really no hope of looking for the supermassive black hole that resides there. So infrared's not good enough. We need very high spatial resolution. Fortunately, we can do that. We have very large telescopes now equipped with adaptive optics, which is a technology we need to correct for the blurring effects of the Earth's atmosphere. In fact, if you built the Keck telescopes and you take an infrared picture of the galactic center, which I'll show you in just a little bit, it will have the same exact spatial resolution as that of a 3.5 meter or even of a 1 meter or less telescope. And that's because the blurring effects of the Earth's atmosphere is what limits our resolution from the ground. Adaptive optics corrects all of that for us. I'll show you how that works in just a moment. So this is a picture of the Keck telescopes, which are located at the summit of Mauna Kea in Hawaii, one of the most exquisite astronomical sites. If you've never been up there, I highly encourage it. It's an incredible experience to get up there. Here's the team, the original Galactic Center team. These are my former PhD advisor, Andrea Ghez, is the one seated in front of the computer, and her 2 mentors on this project, Eric Becklin and Mark Morris. And this was the very first observing, I think actually maybe the second run to observe the Galactic Center from the Keck telescopes. They had to observe from the summit. You can see their old computers, and they were taking images of what we call speckle imaging. You take very short exposures. This was pre-adaptive optics. You take very short exposures and freeze the turbulence of the atmosphere, which is shown in this picture. And hopefully you can see my mouse, but you take a very short exposure, and normally your star would be this big, but instead you get a frozen atmosphere temporarily, get a temporary diffraction limited image, and you can start to resolve and see the small structures for individual stars, but it's very noisy. So we take many of those and heavily process them with computers and construct an image of the galactic center that's high enough resolution for us to start to see individual stars right around where we think the black hole was. And in those early days in Andrea and company's first experiments, they already saw that the stars were moving over time. And on the scale and the distance at which these stars existed, they knew immediately that something interesting was here because the stars were moving faster than you might expect otherwise. Now, to give you a sense of scale, this is arc seconds on the sky. So you're typically used to looking at pictures where, if you're using a small telescope, where a single star takes up an arc second or 2 or 4 or 5. And yet here we're talking about stars that are separated by just a few tenths of an arc second across. Okay, so that was pre-adaptive optics. Our whole lives got better when adaptive optics came along. And this is about the time when I became a PhD student at UCLA. So first, let's start with the picture of the atmosphere without adaptive optics. You get these blurry speckly looking things if you can integrate quickly. So with speckle, we were just taking a bunch of fast exposures like this and then finding the brightest point, shifting it and adding it up to try and recover high spatial resolution. With adaptive optics, instead, what we do is we build a deformable mirror and a sensor that can operate on millisecond timescales to measure the turbulence and apply a correction on the deformable mirror. So if you think about a wavefront of light, if it's perfect, it's coming in flat. It's like a piece of paper traveling all the way through space, unaberrated. It hits our atmosphere and our atmosphere aberrates it. It crinkles it up like a potato chip or a crumpled piece of paper. And that's the aberrations and distortions that cause everything we saw on the left over here. So we make a measurement with our wavefront sensor of those aberrations, apply a correction on this very flexible, very thin, very fast deformable mirror, correct it, and send our corrected light off to our science camera. So when we do this, that we can immediately correct in real time these aberrations and the blurring of the atmosphere and hopefully get back a very sharp image. There's one caveat. For an adaptive optics system to work, you have to have a bright guide star. That just means a single star that you know it's a star, not a galaxy, not an asteroid, it's not moving fast. So a point-like object that's pretty bright, has lots of photons. Unfortunately, if you remember that picture I showed you of the galactic center, we don't have very many bright optical guide stars in that direction of the sky. So we're stuck. So what would we use for an optical guide star instead? Fortunately, some very enterprising researchers and physicists realized you can make your own fake stars with using a laser by illuminating a layer of neutral sodium atoms that are about 90 kilometers up in the atmosphere. The sodium they're deposited actually by micrometeorites raining down on Earth's atmosphere from up above. They trickle down over time, and above this, they're ionized. Below this, they're in molecules. And at this stage, they're just kind of perfectly neutral, 90 kilometers up, and the thickness is about 10 kilometers. We shine a laser tuned to a special frequency to excite those neutral sodium atoms, and they re-emit light back down, just like looks just like a star. So we can now point our laser anywhere we want in the sky, or almost anywhere, I should say, and then use that fake guide star to correct and run our adaptive optics system, even towards the highly obscure galactic center. So what do we get? Here's now the galactic center before we turn on our adaptive optics system. And this is what we get after we turn on the adaptive optics system. You can see the difference is remarkable. You go from a blurry, seeing limited image to a sharp image that's only limited by the diffraction limit of our telescope, which is a large 10-meter class Keck telescope. You can see there's a lot of action in the galactic center. We can now resolve individual stars, lots of dust and gas. And most importantly, we can watch over time as the stars move, which very early on told us that there was a massive object right around where this arrow is pointing. All the stars seem to be orbiting around it. So it's been our great pleasure to now be able to use the adaptive optics systems at both Keck telescopes. We use them routinely. We use them sometimes at the same time, as shown in this exquisite picture. And sometimes even our friends use it too and observe with us at the same time, this is a third laser over here on the other side. And with Keck adaptive optics now, we're able to watch over time. And this is a picture developed from all of our observations of where the stars are moving. So again, you can see back in mid-2000s, early 2000s, when I joined the program, we were just really starting to see the first star curve around what is now known to be the supermassive black hole. And that was the very first indications that there was a dark matter there of some kind. And we spent the next, well, since 1995 up through, very recently, we've spent proving that that is indeed a supermassive black hole and nothing else. The way we prove it is we show that these stars come within about 45 AU, that's a Sun-Pluto distance, of the thing they're orbiting. We've shown, given their periods and semi-major axes, that the stars are moving at about 12,000 kilometers per second, so a significant fraction of the speed of light. And as a result, combining their velocities, their periods, their distances, all together, we can prove that there's about 4 million times the mass of the sun within the volume of our solar system. And with our current understanding of physics, there is nothing, not even exotic quark stars, that can have that kind of density. It's only a black hole. So as a consequence, this has led to the proof, the best evidence yet, that a supermassive black hole exists and resides at the heart of our own galactic center. Now, this experiment has been tremendously fruitful because not only did we show there was a black hole, we've garnered a huge range of other interesting science, including discovering that there is accretion of material onto the supermassive black hole that is glowing over time and changing and flickering as the gas that's falling into the black hole changes, little bits of gas, larger amounts of gas. So this discovery of this variable source associated with the black hole has allowed us to study how accretion of gas onto a black hole changes and is affected by its surroundings. So that's been incredible. And then this is just a sort of summary movie of everything that we've since learned about the orbits of the stars. Not only do we know about their orbits, we also now know what types of stars they are. You can see the blue stars in here. These are hot young stars. The red stars are old and cool stars. And the purple ones are exotic stars that we actually don't know what they are. And we are actively studying why they have the colors and the appearance that they do have. You can also see that the stars aren't randomly distributed around the black hole. You see this disk-like structure. The young stars appear to have formed in a disk, a large disk around the black hole. We have no idea why that is, and we're still studying it. So there's a huge range of new questions that have been raised as a result of that very early experiment just to find the black hole. And more recently, just in the last couple of years, we've gone from proving the black hole exists to using the black hole as a probe. So in the year 2018, one of our brightest stars and closest stars to the black hole, SO2, went through its closest approach. And when it did so, we had all telescopes trained on to the event and made many measurements to try and test whether Einstein's theory of general relativity would break or be consistent with the observations we made of the star. And in fact, at that time, the star was moving at about 3% of the speed of light. And we expected to see a signature in its velocity, its line of sight velocity would actually change relative to Newtonian gravity. And that signal looks something like this on the bottom here. And hopefully this will play. Let's see. Yeah. So this gravitational redshift that comes as a prediction of general relativity is supposed to spike when the star goes through closest approach and then drop down again. And there are further in the future positional measurements too. The orbit won't close due to general relativity, and we're looking for that signal now. But in the past couple of years, we've indeed already confirmed the gravitational redshift, and that general relativity currently is still our best working model for the way gravity influences the space-time around it. So I hope you enjoyed this little summary of our supermassive black hole work. I thought I'd flash up a picture of our team up at the Keck telescopes. I know you probably all have many pictures out observing with your telescopes. Well, this is what we get to do. Sadly, we don't get to go out nearly as often as you do. We only get to go up to the summit once every few years. Most of our observing these days is done down at the base where you aren't prone to altitude sickness and you can keep your head on straight a little bit. So it's really fun to get up there, and this was a special trip for all of us. So I wanted to spend the second half talking about the other variety of black holes. These are stellar mass black holes. Before I go on, though, I'll take a minute and see if there's any questions about the supermassive variety. All right.
I have a quick question. You're looking at these orbits over a time period of, you said, I think 25 years or so. And I'm guessing that you weren't part of that 25 years ago. So how much of this was waiting until finally there was enough trajectory or proper motion data to make some conclusions, sort of a lot of thankless years before that, or were good things coming out of it even before great, large proper motions had sort of been undergone?
Right. So it depends a little bit on who you had to convince and how skeptical they were. So I think some significant fraction of astronomers thought that it was a supermassive black hole after about the first 6 years of the experiment, I would say. So that was in the early 2000s, 2000, 2001. And then there were a series of definitive sounding papers to convince everybody else when I was a young grad student in 2005 and 2006. There were still some exotic theories, like I said, of quark stars and other really unusual non-black hole theories that were still kind of floating around until about 2008, 9, 10, something around there. I think by that time, everyone was fairly convinced. But the program started in 1995 with the Keck telescope. So that first 5 years, it was very, very tenuous. It was probably very tough for the earliest researchers in the group, including Andrea Ghez and Reinhard Genzel.
All right, yeah, that's very interesting. And then, so with further observations, once you've sort of convinced everybody, I'm convinced at least. What do you get from further observations now? Are you refining the mass or what?
Yeah, so the further observations is really about testing theories of general relativity. That's the first item. So today, what we've done is measured the gravitational redshift, and Andrea's group at UCLA and I included are continuing to work on measuring this periapse precession portion of the prediction of general relativity, and then we need to observe it. So that's one thing in terms of tests of general relativity. The other thing that we're excited about is there is supposed to be not just a black hole, but dark matter, sort of a cusp of dark matter that's sunk in and focused on the black hole, surrounding the black hole. And that hasn't yet been detected. There's some tentative signs. We're starting to get into the regime where we can detect it, but that's what we're kind of all actively working towards now. And then finally, the last thing that I particularly am excited about, not only should there be a supermassive black hole and dark matter, there should also be a sea of stellar mass black holes, old remnants that have sunk in from the larger galaxy. So you can see everything odd that can happen does happen at the galactic center. And so now we're starting to look for signs of that other unusual population.
Interesting. Great. Thanks.
There was another question. I saw Greg Lee raised his hand. Greg, do you want to ask your question?
Yes, I was looking at the elliptical orbits of some of these stars in the illustrations, and I'm wondering if the observations have shown any perturbation in those orbits where they might get shifted a bit and actually observe a star being drawn into the black hole, or at least some gas being pulled off of the star.
Yeah, that's a great question. So actually, I think let me get to this movie. Yep, that one. All right, so this is going to play here. So if you look at one of these pink objects, a few years ago, we saw one of these pink objects that looked kind of like a puffy gas cloud heading in towards the center. And all the astronomers, we all got very excited. We thought it was a gas cloud that was going to be shredded and ripped apart by the black hole. But in fact, much to our surprise, it stayed together. And so it looks like it's not a gas cloud, but actually some kind of extremely unusual star. We don't really know exactly what it is yet. It hung together. So that was our most promising object for looking for a deviation from that sort of elliptical classical Keplerian orbit. And to date, we still haven't seen one. We are looking for signs of binary stars, just regular binary stars oscillating, but those are very tiny oscillations relative to these big orbits that you see. So far we're on the hunt for those deviations from the pure ellipse, but we haven't yet found them. Okay, so let's see. Let's go on to the stellar mass black hole variety. Let's see, apologies, I have to get through this. Okay, so now let's talk about the stellar mass black holes. Remember, these are the black holes that are produced when a massive star dies. And we do know of a few of these in our own galaxy. We can see them, mostly with this artist's rendition that you see a donor star is expanded, it's gotten very fluffy to the point where the gravity from the black hole is about the same as the gravity from the star itself. And that leads to mass coming off of the star and flowing down onto the black hole, and the black hole is usually spinning and the two objects are orbiting. So there's this accretion disk that forms. The material migrates inward through this disk and dumps onto the black hole and falls into it and produces a lot of light just before it passes through the event horizon of the black hole. So we can certainly see these kinds of black holes in our own galaxy. And as I said, there's a handful of these that are known. Nowadays, we can also hear black holes, so to speak, that's in quotes, because this is the new gravitational wave signature, which is not an electromagnetic signal at all. It's not from light, not from photons. It's the ripples in space-time that have been created when two black holes merge. They produce these ripples, which then propagate out into the universe and eventually reach our detectors like LIGO and Virgo. These are gravitational wave detectors that have just come online in the last 5 years or so. So this is a totally new way of probing the universe that we've never had access to before. And so that's allowed us to astronomers to detect these merging black holes, quite a few of them now, in fact. But you notice that all of these black holes, the ones we see and the ones we hear in air quotes, are all in binaries. So this is actually now an outdated picture of all the binaries that have, all the black holes of the stellar mass variety that have ever been detected. So these are all in binaries. The blue ones are the gravitational wave detected black holes. The purple ones are the electromagnetically detected black holes. And all but maybe 5 or 6 of these purple ones are in other distant galaxies. Only the 5 or 6 lowest purple ones are in our own galaxy. So that leaves us with a lot of unanswered questions about black holes in general, right? If all we ever see are the ones that come in pairs, we can't answer even the simplest things, like what are the total number of black holes in our own galaxy? Remember, I told you before, it's somewhere between 100 million and 1 billion. It's actually uncertain by more than an order of magnitude. We don't even know how many black holes are in our galaxy. It turns out we're not so sure even what types of stars turn into black holes. I said it was something simple, like bigger than 20 or 30 times the mass of the sun. But in fact, we're seeing some data that says that it's not that. It's sometimes they turn into neutron stars, sometimes they turn into black holes, and we don't know when or why or how. We don't know the black holes that do form with what their masses are. Are there, are all black holes 5 times as massive as the sun? Are they 10 times? Is there a big distribution? We don't know how many black holes are in binaries and which ones will merge. That makes it exceedingly hard to interpret those LIGO and Virgo results, to make sense of them. We don't know if black holes get kicked during the violent birth, the supernova explosion, which is the death of the star. And we don't know if something even more exotic out there exists, something like a primordial black hole. This would be a black hole born at the beginning of the universe during or immediately after the Big Bang, during inflation. You can, in theory, get primordial black holes to form and last all the way through until today's modern times. To answer all of these very major questions about black holes, we're missing one key ingredient, and that is finding the population of isolated black holes, the ones that are just free floating, which we think is the majority, right? So we found in our galaxy a few 5s, 10s of black holes all in binaries. Where are the 100 million to 1 billion other black holes in our galaxy? So that's what we're on the hunt to do now, is to find free floating black holes within our Milky Way. Now, like I said, they're plentiful. There's tons of them. If you just went out and looked out at the night sky and held your thumb up, within your thumb print on the sky, you should be seeing 10s, maybe 50 black holes. So just to give you a sense, this is in arc seconds again, 20 arc second patch. And in one random 20 arc second patch, you're very likely to find a black hole. So your thumb's about 1/2 degree. So we're talking about 150, 10s to hundreds of black holes in that one little spot, depending on where you go, especially if you're putting your thumb on the galactic plane or the bulge of our galaxy. So how can we find them? They're there, they're plentiful. We have not yet found one. Well, we have to play a trick. We have to use not light coming from the black hole or a companion, but instead its effect on the space-time around it. And we can use it as something that's called gravitational lensing. So the black hole can act just like this wine glass. It can act as a lens to warp light rays coming from a background star. So you're in the evening there, so you can grab your wine glass and hold it up and in front of a candle or a light bulb, and you should be able to see, if you align it just right, you should be able to see a ring. So your candle, your picture of your point source, turns into a ring. Or you should be able to see multiple images that get produced. Sometimes 3, in this case 2, and they get a little elongated. So a black hole does exactly the same thing when a background star passes behind it. It gravitationally lenses it and produces multiple images, or if we're really lucky, a whole ring, right? So that's the effect of gravitational lensing. We see gravitational lensing in the universe all the time. This is a couple of examples of exactly that same effect. But these are whole galaxies lensing whole background galaxies or background supermassive black holes. That's not what we're after. We want these are very, very distant objects. We want the lenses that are occurring from small black holes in our own Milky Way. So that's kind of what we're looking for. This is the effect that we're hoping to see, but this is wildly zoomed in if we could be very close to the black hole. Unfortunately, the effect that we can actually observe is far smaller than that. But this is the exactly what gravitational lensing will do to the background light. Okay, so let's put this into a little more quantitative context here. So we have a background star, we have our foreground black hole. It produces these lensed multiple images, and then that light comes down to our telescopes. Unfortunately, for stellar mass black holes in our galaxy, the picture that we take, we don't see the two separated images. They're just too close together. They're separated by milli arcseconds to micro arcseconds. So we really just see a single object on the sky, and we call that microlensing, gravitational microlensing, rather than macro or just lensing. So what can we do? If it just looks like one star and we don't see the two images, how will we know we have a black hole? Well, fortunately, gravitational lensing does 2 other things that we can detect, even if we can't see the 2 images separately. So first, here's the black hole in the middle. The background star is passing by in red, but what we actually see is the lensed light shown in blue. We can't resolve them, but if you sum up all of the flux, all of the photons coming from inside a big circle, which is like our telescope aperture, then what you'll find is that the photometry, the brightness of that object, changes with time. It doesn't stay constant like most stars do. It will brighten temporarily and then fade away again in a very characteristic and pretty symmetric signal. This is almost nothing else in the universe will look like this gravitational lensing signal. So we can use photometry alone to go and look for microlensing events. Unfortunately, it's not just black holes that act as lenses. Stars act as lenses too. So we need some way to distinguish when we see an event like this, is it a black hole or is it a star? How do we know? Well, we need some estimate of the mass of this object. And so this light curve by itself doesn't give us any mass information. So we need a different type of measurement besides just measuring how bright the object is over time. So the second thing we do is we use astrometry, the measurements of the positions of stars. So again, the black hole is here in blue. The actual background star's trajectory is in green. The 2 images that get created are these yellow lines. But again, if you add them all up and now you don't just measure the flux, but you measure the position, you'll find that the position looks offset. It's this red line. It looks offset temporarily. So instead of the star moving in a straight line, it actually wobbles off its path for a little bit and then returns after the microlensing event is done. And the beauty of this astrometric signal is that the offset, the size of this, tells you the mass of the lens right there. So with this joint photometry or brightness measurement and astrometry or position measurement on the sky, we can then get the mass and infer whether that lens is a black hole or something else. So this is simulated data. This isn't real yet, but this is what a simulation of the observations would look like. So this is the kind of signal we're looking for, right? A really tiny deviation from linear motion. And the size of the effect is tiny. For a black hole, which is this black curve here, if you look at the size of that astrometric signal, we're talking about milli-arcseconds. Again, even our sharpest telescopes have resolutions that are 100 times, 50 to 100 times worse than this. So we need to get way, way, way better precision at measuring the position than we have the resolution to see. And this is for a typical 10 solar mass black hole at 4 kiloparsecs with a star at the galactic center.
Jessica?
So yeah, go ahead.
Rick, do you want to jump in with your question at this point?
Oh, so yeah, so I guess you need some proper motion to detect lensing. You really can't.
Indeed, you do.
Pattern, okay.
That's right. Otherwise, this star would stay bright and stay in its offset position at all the time. No, it would not look like a transient signal. So indeed, we need some motion between the two.
When you look at like the popular, Sky and Telescope magazines, they show these nice pictures of these not quite circular rings, as you showed with the wine glasses, with some breaks in them. And it kind of makes you think that you get that from a static image, but evidently not, because that could be due to anything, I guess.
That's right. In the galaxy's case, there is a lot you can learn from the static image by seeing the multiple images. But for our case, since we can't resolve the microlensing event, we don't have the multiple images, there's not much we can do from a static case. We have to have that transient nature for us to infer anything useful out of the lensing event.
Is that a big problem, or is that not a big problem? I mean, how many stars have enough proper motion? I mean, they may not be lensed.
Yeah, so fortunately for us, at least in the Milky Way, everything moves and moves with enough of a proper motion for us to see it in a human lifetime, or even in a PhD thesis lifetime.
Okay.
The duration of these events is usually between tens of days, but for the black holes, it's typically more than 100 days, but it's not much more than 100 days.
Right.
So, we're patient. It's definitely a long game. You have to wait many years because you have to measure both this signal and the baseline signal. So we typically have to observe each target for at least 5 years.
That's getting up there for a PhD thesis, assuming they have to take classes.
Yeah, exactly. Good. Other questions?
Sheila, do you want to ask your question directly?
Sure. Yeah, I was wondering if there's a lower limit to the mass that's required to make gravitational lensing happen.
Yeah, so all objects with mass produce a gravitational lensing effect, but most of the time it's too small to see.
Yeah, I guess I should have asked observable gravitational lensing.
Yeah.
Maybe is a better way to put it. Yeah.
Yeah, so actually planets around planets around stars, or even free floating planets, can cause detectable lensing signals in the photometry. In the astrometry, it's not so good yet. We're only able to really, hopefully soon, we haven't detected this yet, but to find a black hole, a very massive lens. For the photometry, we can see all the way down to planets now. And with our next generation Roman observatory, which is a space telescope, we hope to be able to see something like lunar mass objects gravitationally lensing.
Oh my God, that's incredible. Thank you.
Yeah. Yep. Oh, you're muted, Jeff.
I don't see anything else coming in at this point, Jessica, so.
Great.
Also somebody by the name of Becky that said something. I don't know if it was a comment though. Becky? Not sure. Okay.
Okay. All right, I'll keep going. There's more time for questions at the end. Okay, so black hole microlensing is rare. So you have to have this nice alignment between the star and the black hole, and it's hard to measure. So we need to know where to look. We can't just observe the whole sky and find it at any time. We need to know what the signpost is. But thankfully, we can do that because there are wide field photometric surveys that are covering almost the whole galactic plane, but they focus mostly on the center of the galaxy. These are surveys like OGLE and MOA, and they use dedicated 1 meter to 3 meter class telescopes, and they just stare every single night towards the center, and they make a measurement of the photometry of several tens of millions of stars. So they're making measurements that look like this. That looks like microlensing. That's what we want to see. So we go and look at their catalogs, about 1,000 events per year, and we go find the ones that we think are black holes. And then we start to make our astrometric measurements. We need to identify them before the peak, and then we need to measure with our Keck telescopes, our high precision astrometry machines, just like we used on the Galactic Center. We measure them from starting from the peak all the way down and many years into the future. So how do we know which ones are good black holes, good black hole candidates? Well, it turns out we've done a lot of sort of population synthesis. That's simulations in a computer of what the Milky Way looks like with black holes and microlensing. And it turns out that the time scale of that microlensing event is a key way of finding black holes. So on this horizontal axis is plotted the time scale, how long the microlensing event takes. And you can see in this simulation, I've marked up where the stars are, the white dwarfs, the neutron stars in orange, and the black holes in black. And so the black holes like to be long time scale events. So we go and pick out long time scale events, things that are over 100 days, and those provide us about 10 good black hole candidates to start observing each year. Then we point our Keck telescopes at those and make a few, 5 measurements the first year, 2 or 3 measurements for every year after that for 5 years. And we hope to see an astrometric lensing signal. So there's the photometry. Here's the astrometry we've got for a star so far. For this one, unfortunately, you see it moved in a straight line. No signs of an astrometric signal whatsoever. So for this star, we could prove it was not a black hole. This was the very first time we'd ever attempted this experiment. We didn't get lucky, unfortunately, but it's pretty typical for experimental work like this. So it was pretty cool, though. We could, oh, my apologies. Sorry, we could constrain the mass of the lens object. We could show you that it was not a black hole. It was a small mass object, less than 1.2 solar masses. Probably your run-of-the-mill star, maybe a white dwarf or a neutron star. But for us, it wasn't a black hole, so we kind of moved on to other objects. So we're continuing to make these measurements. We have about a sample of 10 that we're currently monitoring, and we have some very promising looking results coming out, but we're right on the cusp. This is very challenging technically, but you should look forward to the news items soon where we discover black holes using this astrometric microlensing technique. So as I said, it's right on the cusp of technology. It's very dependent on adaptive optics. So we're always, I always work on improvements to adaptive optics as well. How can we make better astrometric measurements? And so we're constantly working on improving adaptive optics. We're upgrading the Keck adaptive optics system now that would improve our image quality from things like this red line to things like this blue line. And that would help with our discovery of black holes. We could reduce the time that it takes and what kinds of objects we could find by a significant amount with these kinds of improvements. These kinds of improvements are also incredibly powerful for studies of the Galactic Center. This is a picture of the Galactic Center today with our current AO system. This is a real picture that we've taken at infrared wavelengths. And here's what we'll get in just a couple of years with these upgrades to the Keck system. And then lastly, we're really looking forward to building our big next generation of telescopes. One in particular is called the 30-meter telescope. Here's the size of the Keck primary mirror. You remember that picture, how big it was relative to the people. Just imagine this kind of a telescope. Incredible resolving power. And here's a picture of the Galactic Center today, in just a few years, and then about 10 years from now, when the 30-meter telescope has first light, we can start to measure all the stars orbiting the supermassive black hole there. So these future upgrades to our facilities will allow us to detect not only black holes, but also neutron stars, study the stellar population at the Galactic Center, test Einstein's theory of general relativity, and all in all, hopefully make these black holes out in the universe just somewhat less mysterious than they are to us today. I'd like to say thanks. Of course, this is all a huge endeavor by a tremendous group of people, both on the Galactic Center group at UCLA and Keck Observatory, and my microlensing group at Berkeley and collaborators beyond that. I'm happy to take questions now, and thanks again so much for the opportunity to talk to all of you.
Yeah, Jessica, thank you very much. That was excellent stuff. Yeah, at this point, let's maybe strip off a layer of formality, and if anyone has any questions or comments, by all means, unmute and ask away.
Okay, I have a small technical question. You showed photos of the observatories with the sodium lasers, I guess, going out. Or though, is that an art addition to the photograph, or is that really how bright the laser is, that you can see it scatter off of the atmosphere?
Right. Yeah, so those are long exposure images at nighttime. So if you go stand next to the telescope, you can look up and see the laser at low elevation, but you can't see the spot that it makes. So the artificial star is too faint for our eyes. But that, what we call a Rayleigh scatter at low, where the air is still thick in the atmosphere, you can see that. It's pretty faint, way fainter than the picture shows.
Okay.
So that picture was taken with a long exposure on a digital camera. We do have to worry about the neighbor telescopes seeing our laser in their pictures. So there is a coordination for when a laser is going to intersect the path or the image of another telescope, and we have to coordinate all of that throughout the night continuously.
Interesting.
And the other question, we've heard also about adaptive optics based on actual stars. Do you not do that at all because you have the laser adaptive optics? Is that, or do you do regular star adaptive optics?
Many people, especially those who are hunting for exoplanets, do use the regular natural guide star adaptive optics. But for all the work that I do, I'm always doing the hard stuff. I'm looking deep into the galaxy where everything's obscured, or in distant galaxies where the stars are not resolvable, or in crowded stellar fields where we don't have, we can't get out a single bright star. So all of those experiments require the laser. So for my part, I'm almost exclusively a laser guide star observer.
Okay, if you had an actual guide star instead of a laser guide star, is there any advantage to it?
Yeah, that's a really great question. Let's see if I can get back to one of the slides that will show you one of the disadvantages of the laser guide star. So you can see the laser is not at infinity, so it doesn't actually sense the full cone of the atmospheric aberrations that the normal starlight passes through. So that can lead to, we're missing this piece. This is with a laser drawn off to the side, but you can put it in the middle and infer the same thing. So you kind of miss a little bit. And that's something we very not creatively call the cone effect. And so, yeah, our laser images don't have as high a quality as the natural guide star images. But one of the upgrades we're working on is exactly this, is getting rid of that by having multiple lasers and filling in that volume. We can do tomography, just like you do brain imaging tomography. You look from many angles and you reconstruct the 3D structure of your brain. We're going to do the exact same thing with the atmosphere, multiple lasers all around, and then we can do tomography and reconstruct the full cone of turbulence. And that will bring our laser images up to the same quality as our natural guide star images.
Okay, thank you.
It sounds like some pretty fast computing for that, because I guess that tomography has to happen on the time scale over which you want to deform your mirror.
Absolutely. So in fact, part of the upgrade project that's being delivered and installed right now at Keck is a new real-time control computer, which is a massive computer with some very, very carefully designed algorithms implemented often with GPU acceleration to try and do this tomography on millisecond or even half millisecond timescales. Yeah, it's a challenge.
The way you've drawn this, you see the cone, but I thought the way you described it, it sounded like the issue was that the sodium layer that you're exciting is not as far away as a star. And so you're losing the effects of turbulence above that sodium layer, and tomography wouldn't solve that.
So the turbulence above, so at 90 kilometers, there's not much air above the sodium, above the laser. So it really is just the little bit below the laser in the cone that you're in the cylinder that your laser cone doesn't sense. It's really down a little bit lower, just below the sodium layer that we're concerned. So it is that cone effect predominantly.
All right, got you.
Dr. Liu, I had a question about, you said that a lot of ways that we measure this is within the electromagnetic spectrum, but you also talked about how we're now measuring, the sound of it. Is there any future about detecting black holes in the mechanical wave, or like any future with that? Or is that kind of, there's too much noise, there's no future in it? I have been explored.
Yeah, so the hearing, it's not really in sound waves as our ears can hear them. It's space-time ripples, but it just so happens that the frequency at which space-time is rippling that LIGO can detect is in the same frequency that we hear sound. So you'll often, if you go hear a gravitational wave talk, they'll play a zzz noise for you that is the merger of the two black holes. But it is not in a spectrum that we can hear or see. It's only in a spectrum that our clocks can sense, so to speak, or our rulers can sense. There is no other, as far as I know, no other sort of mechanical means of seeing black holes effects other than through its gravitational influence on the light and its gravitational influence on space-time. Other than if you're accreting, say, matter into the black hole, and maybe you could see the accretion luminosity, but again, that's just a light probe. There's some speculation that for things like the Large Hadron Collider, you could potentially produce black holes and see their evaporation. That's very speculative and usually on sort of fringe theories of physics, but in principle, it's possible.
Very
Not
cool.
my
Thank
field
you.
of expertise at all. Yeah.
Awesome.
In one of your first slides, I recall seeing that the black holes are produced by stars with a roughly 30 stellar mass. And yes, this. And they turn into holes with a roughly 3 stellar mass. Is that all that material blown off in the supernova, or how does that happen?
Yeah, so for these very massive stars at the end of their life, they are sloughing off their outer layers. So a star will typically lose something like, these massive stars may lose up to half its mass well before the supernova. And then the supernova itself, you lose a lot more again. And this ratio of the initial mass of the star to this final black hole mass is wildly uncertain. So that's really what, if we could find these isolated black holes, we could start to try and constrain that. We call that the initial final mass relation, how the birth mass is related to the remnant mass afterwards. Yeah, so I've drawn it here as sort of 30 to 3, but we don't know that that's true at all. It might be that 20 and 30s never produce a black hole. They only produce neutron stars, or they could produce low mass black holes, or even higher mass black holes. We simply just don't know.
Thanks.
There was a question, does the flexing of the mirror with the adaptive optics, does that wear it out?
Yeah, so these deformable mirrors are incredible feats of engineering, just really amazing. So the Keck deformable mirror is only about 10 inches in size, but it packs a whop. It's got tons, hundreds of actuators on the backside poking little bits of the mirror. And it has to happen, has to fluctuate on millisecond timescales. So obviously that's a mechanical and electronics device. You'll see it looks like a Hydra head with hundreds of wires coming out the back. It's pretty spectacular. And they wear out, but amazing to us, they've actually stood the test of time pretty well. Keck's deformable mirrors, it's had 2 of them. They've been operating for more than 10 years with relatively little maintenance. Every once in a while, one of the actuators, the things that does the poking, will freeze or stop responding in the way that it should. And so then they may have to replace one of those. But the mirrors that they've made so far are incredibly robust. But we're still working to develop new mirrors that are larger in size, that could replace a whole telescope optic, like the secondary on the telescope, or that has many more actuators packed into the same mirror size, or that runs just faster and faster, or that can poke more. So all of those are still advances in the engineering side of things that we're still working on in the astro technology side.
with airspace and airplanes, do you have to get any permission or let anybody know about your lasers going up because of aircraft?
Yeah, great question. So we are shining lasers up into the sky, and you've probably heard of commercial consumer lasers and problems at airports. We have something similar. There's actually in the United States a laser clearinghouse. It's called, well, there's two of them. There's two different ones. One, we have to deal with airplanes. So we are under strict regulations. We have to be constantly monitoring for airplanes. And if an airplane comes with anywhere close to the space where we're shining the laser, we have to immediately shut the laser. These days, that's an automated system using the airplane transponders. So we have on the back of our telescope a transponder detector that listens for all the airplanes around. And if it hears one and it knows where it is, then it shuts the laser down automatically. That's pretty rare in Hawaii, but Lick Observatory has a laser, and they used to be on a flight path for flights out of SFO, San Francisco Airport. And so that used to be a major problem for their AO system. We have a second thing we have to worry about, which is satellites. So in principle, our lasers shining up could blind a satellite looking down. And so we also have a space command, which we have to submit and ask for permission to shine our laser at various points in the sky at various hours in the night. And sometimes, well, frequently, they come back and say, sorry, you can't look there. And apparently, they were wise and decided to throw in random dark spots where we couldn't look so that we wouldn't be able to use our closures, our laser closures, to track satellites. So they send us a bunch where real satellites are going by and a bunch where probably nothing's going by. It's just to fake us out. But during those times, we can't use the laser at that area of the sky.
Crazy.
And the laser's on continuously, correct? Running.
So we have a shutter in front of it. So it's on an optical bench somewhere in the telescope, and we open it up and shine it, launch it up into, with a little tiny telescope itself, we launch it up into the air. And it's not always going. It's going always when we're taking science data, but then we can shutter it and stop taking science data for a little bit and then turn it back on again and start taking pictures again.
Right, but yeah, as long as you're taking data, the laser is on, right?
That's correct, yep.
Yeah, okay.
Thank you.
Mm-hmm. And if you like lasers, we have there's a new project that's being spearheaded out of NASA Goddard, where they're going to try and launch a small satellite to host a laser. The laser points down, and now it's just a fake star that you can fly around in the satellite and move the satellite around where you need it and point your telescope at it and wherever your interesting science object is. So it's nice because it looks like a real star. Now it looks like something almost at infinity, not down low where the laser is. So you get rid of that cone effect. You can make it way brighter. You're not restricted to how much sodium is in that layer. The downside is you can't move it anywhere in the sky very quickly. So you have to think far in advance where that satellite's going to be at exactly the right time. And you have to get very creative with the satellite orbit, because if you've ever went out to the night sky and looked for satellites, they zip across the sky very quickly. Not so useful for deep observations of the universe. So they have to put it on a creative orbit to get it to stay relatively fixed on the sky for a little while, for a couple hours at least. That project is called ORCAS, if you ever want to look it up, ORCAS.
What? I'm sorry. What's the creative approach to keeping the satellite stationary? Because obviously it's not geosynchronous.
Yeah, so it's a very elliptical orbit. So when it's far from Earth at its apo distance, it stays kind of still, not very still, not perfectly still, but it's still enough for a couple of hours. And then it zips down through, and that orbit processes like a flower petal over time, so you can cover different parts of the sky.
Oh, okay.
When you were talking about the massive black hole at the center of the Milky Way, you showed a screen that showed a lot of stars that were orbiting around the black hole, and they sort of formed a disk. Is there any Is there any relationship between the axis of that disk and the axis of the Milky Way itself?
Yeah, very good question. Thankfully for us, not so much, because otherwise it would have been incredibly difficult to detect it. So it turns out this disk of young stars, by young I mean 5 million years old, but that's young for a star's lifetime. This disk of young stars is actually tilted with respect to the galactic plane by about 90 degrees. So it's
really?
very, very
No
off of the
kidding.
plane. Yeah.
Wow.
Okay, that's interesting.
Yeah, there's all kinds of planar structures. It's not so much in this picture, but there's a huge ring of gas in the center of the galaxy too, right around the black hole. And it is also tilted by about 30 degrees, which is very, very fortunate for us. Because if it weren't tilted, if it were in the galactic plane, even our modern day infrared telescopes wouldn't have been able to see into the middle. It would have given an extra several magnitudes of extinction or obscuration that we wouldn't have been able to see through. We would have had to have waited until the next generation of telescopes to peer in past that gas cloud.
Okay, thank you.
The stars that you identified with purple and said were unusual, what made them unusual in that area?
Yeah, so these objects, if you want to Google search them, they were called G2 or G-like objects. These were they were originally thought to be gas clouds. And we thought they were gas clouds. Well, some astronomers thought they were gas clouds because they were very red and a little bit larger than a star. We could actually see that they had size to them, which at that distance, that made them quite large. And so that very red, puffy, gassy, dusty look to them and their resolved size initially suggested that they might just be this kind of fluffy, nebulous gas cloud that would be torn apart when it passed close to the black hole. But then what happened is it passed close to the black hole and it stayed together. It looked almost exactly the same afterwards as it did before. So that suggests that there is a puffy gas cloud there, but there's something in the middle, of a star or a white dwarf or neutron, something we don't know that's holding it together, that prevented the black hole from pulling off the fluffy gas part of it. Other questions?
Any final questions?
I would like to say, though, that was a spectacular talk. Thank you very much.
Yes, thank you. Yes,
Yeah, that was really
fascinating.
stupendous. And,
Yeah, thank you.
I think we all
I'm
want to
happy
be
to.
here.
Yeah. Well, believe it or not, that microlensing, that gravitational lensing I mentioned, we actually have a lot of contributions from amateur astronomers very frequently to that field, using their small telescopes to fill in that time domain nature of the object. It means it's critical. We don't have enough telescopes looking all the time to catch these cool phenomena.
Have you ever met Hilton Lewis?
Absolutely. Of course, Hilton's the current director of the Keck Observatory, so I very much know Hilton.
Know him well.
Yeah, great.
Mount
Then you have an in. You can go get a tour of the Keck telescopes on Mauna Kea then.
Been invited many times. Mount Cuba Foundation provides a large amount of grant money to Keck. You probably use some of my equipment that I've helped pay for.
Absolutely, yes. In fact, we do, and we're so grateful because one of the things that I've talked about it with astronomy technology, it really is all of this frontier where it's pushed by the technology developments. Every little thing we discover is really because of the new tech, and it's actually quite challenging in the United States to continue adaptive optics development. The technologies gotten expensive, but it's also just it takes time and dedication to become expert at it. It's really complex, very, very systems architecture, systems engineering, and that can be very challenging today. So we're always trying to push the edge with the technology so that we can push the edge with the astrophysics too.
And I'm sure you know that AO actually was classified and started off for observing satellites.
Indeed, and in fact, it's come back around again. There are groups in Australia that are now using adaptive optics to shine lasers up to target satellites now, not just to, yeah. So there's all kinds of military history and current military applications for adaptive optics, but we astronomers are the cheap country cousins.
We benefited
by
the military came up with.
Yeah, it'd be great to keep those connections, but you'd be surprised the number of times that we've been working on a new adaptive optics system where we deploy duct tape in the middle of the night to to make things work. So we scrap by.
Is the Air Force still operating that telescope that's pretty close to Keck up on the summit with the barbed wire all around it?
So that telescope's on the summit of on Maui, not on the Big Island. So yeah, they're close to the new Daniel K. Inouye Solar Telescope on Maui and Pan-STARRS telescopes, and they still operate. I think they have a laser guide star adaptive optics system. I think they use it a little bit less, but recently, well, not that long ago, now maybe 5 years ago, they were using that system to image the bottom of the shuttle before it would descend to ensure that no tiles came off.
Yeah.
Oh,
so AO is
interesting.
used not just for AO, but also, yeah, for all kinds of other purposes. In fact, adaptive optics is now used to image the human eye.
Yes.
So if you go to an eye doctor, sort of a high-end eye doctor, they can measure the shape of the aberrations in your eye, exactly the same way we measure the shape of the aberrations of the Earth's atmosphere. We're now starting to use adaptive optics for biological imaging to image cells in a flowing stream of blood. So they're all, anytime you have a situation where there's time-dependent aberrations, adaptive optics might be useful for you.
Right.
Nice.
Really cool.
I guess, Jessica, maybe just to fill you in on, to fill in on a comment that David made. So the Delaware Astronomical Society dates back to the late 50s. It actually really was originated by a bunch of scientists and engineers at DuPont that were getting together, and however many decades later, we're still going strong. But yeah, the Delaware Astronomical Society is a group of amateur astronomers. But in parallel with the Delaware Astronomical Society, there's another organization, which is Mount Cuba, which is both an organization and a physical observatory, which is the home observatory for the University of Delaware's research. And the two organizations, there's a lot of overlap and a lot of parallel. They both kind of started around the same time, but the Delaware Astronomical Society is more the amateur side of things, where Mount Cuba is more the professional side of things. So,
got it. Yep.
Yeah.
Yeah. That's great. I think it's a really unique and special place to bring both together. That I wish we could do more of that. It's actually quite challenging in a lot of situations to bring together professional astronomers and amateurs. Especially, you see the lack of it when we professionals get out at night and somebody, our friends like, where is such and such? And we're like, I don't know. I just tell a computer, go point here.
Well,
yeah.
There's also the third organization, which is Mount Cuba Astronomical Foundation, which is the second largest organization for giving money for astronomical research besides the NSF.
Wow.
That's impressive. Yeah.
We make a lot of contributions to Keck.
Absolutely. Yeah. And we've actually had a Mount Cuba Foundation to develop a new style of AO system that covers a very wide field of view, a project called IMACA. So yeah, we're very, very familiar and thankful that the Mount Cuba Foundation exists. And that's why it's such a pleasure to come and give a talk here too, just with this connected organization. It's great.
Nice. Well, we appreciate that you came. It was a great talk.
Oh, it was terrific. Thank you.
Yeah, fantastic.
No problem. And you probably have my email address, so feel free to email me with your questions anytime.
Excellent.
Thank you, Jessica.
Thank you. That's very generous.
Thank you.
Cool. Thanks again. Yeah, and everybody, hopefully we'll see you in one of the astronomy workshops. Otherwise, we'll rejoin the third Tuesday in May to hear Judy give her talk, And then again, another little pitch for think about if there's a mini talk you would like to give at the June meeting. But otherwise, we'll see everybody soon. And obviously keep an eye on the groups.io for any other activities that happen in between us getting together. So have a
Cool.
great night, everybody. Hope to
All
see you
right.
soon.
Thanks. Great to see everybody.
Everybody.
Night.
Good night.
Night.
Night.